Welcome back. And we're almost going to finish the chapter. I keep saying we're going to finish. We're going to circle back and discuss the section right before this one. First thing, next lecture. And it's related to this first part of this reaction. This here is called a quaternary ammonium salt. And there's a section devoted to those. And this is a good way to make it. And quaternary ammonium salts have more use than just here. Salt. Salt is cation, anion. It's not what you think, like table salt. So any ionic compound is called a salt. And what happens here is we put as many methyl groups on this nitrogen as possible. And the words that depict that are here: exhaustive methylation. Exhaustive just means do it as many times as you physically can. So after you do it one time, here's the first time in the mechanism. Backside attack with this nucleophile. Methyl iodide is the electrophile. It's getting attacked. There will be an equilibrium here. It's an equilibrium where the iodide deprotonates the ammonium ion, and now it's another nucleophile ready to go to do the same thing you did the first time. And this would actually draw this equilibrium away from an equilibrium by consuming one of the products. So even though it's an unfavorable equilibrium, by reacting it, you're removing it from the equilibrium, and Le Chatelier says you're going to have to make more of this to make more of this. And what happens after that is the iodide here is going to be reacted or gotten rid of by precipitation right here. So you've generated two iodides if you're keeping score. You made one here. Oh, then you made it react to make HI. And then we generated another iodide here. So then we've only got one if you're keeping score. And then this is a traditional Chem1 precipitation reaction. You didn't do a mechanism back then. I minus donates lone pair, makes silver iodide precipitate. The chemicals added in step 2, you'll see here, are Ag2O. Ag2O, silver oxide, and you put it in water, and it does what most ionic compounds, well, no, not most, a lot. They ionize. You get 2 silver ions, and you get this very reactive oxide ion. That's the conjugate base of hydroxide, which is already a strong base. So it doesn't want to stay like that. And the oxide ion will react with the water because it's done in water. And it picks up a proton and becomes, what's this mean? 2 OH minuses. What? Oh, the water, OH becomes OH minus. And the O2 negative oxide ion deprotonates water and becomes a second hydroxide. So you're making 2 of the same molecule from different approaches. One is this loses a proton, so it acts like an acid, loses a proton to become hydroxide. And here, O2 minus is a base that picks up a proton and becomes hydroxide. So what's going on? Where are we? We've exhaustively methylated to get to this point. And then the iodide gets removed and exchanged for a hydroxide. So that's why this step's called ion exchange. Iodide now has hydroxide in its place to balance the charges. There's your new salt. New salt. And here's your precipitate, gone for the day. And what happens is, upon heating, hydroxide does an E2 reaction. Hydroxide being a base, so we need a molecule that's got a leaving group, and we've got that. An ammonium ion is a good leaving group. It leaves as a neutral amine. Ammonium ions are the conjugate acid of amines, and they have a pKa of 10. So the conjugate base of an acid with a pKa less than 12 is a good leaving group. I'm going to write that down just as a reminder. The conjugate base of an acid with a pKa less than 12 is a good LG. Yeah, pKa subscript. That's not new. Okay. So this was a good LG. It's the conjugate base of an ammonium ion, pKa 10. Same story over here. And what happens during an E2 is you make a pi bond and the leaving group leaves. Ha! So here's the mechanism over here. We got major and minor mechanisms, and they're counterintuitive. You would generally predict that the major would be a pi bond with more hyperconjugation, right? That's your natural tendency. So you're saying there's got to be a typo here. It says minor for the alkene that's more substituted and major for the alkene that's less substituted. That goes against everything I've ever learned. Well, you've also learned what you were just talking about was thermodynamic stability. Okay, so thermodynamic control would create the scenario you just talked about. But this reaction is not under thermodynamic control, it's under kinetic control. And under kinetic control, the more easily approached hydrogen that's beta gets attacked first. And which one's easier to get to? This hydrogen on a carbon with an ethyl and a CH2 nitrogen, or this hydrogen on a carbon that has a CH2 nitrogen only and no other groups? Which one's easier to get to? The answer is right here. The less sterically hindered beta H will create the major product, and the more sterically hindered beta H will create the minor product. So this is under kinetic control, which often involves steric hindrance factors. It's not the first time we've seen it, is it? And here's a Newman pictorial representation of the same story. We're going to try to grab this black H here, and there's this bulkier group up here. It's kind of in the way. And same, well, different H in the same molecule from the other side. This side here, there's no ethyl group up here. It's an H, much tinier, much easier to get to this. So Hoffman elimination. You want to see an exam question, don't you? Exam type question. Predict products. So we'll have a molecule like this. We'll do one that has a little bit of everything. And we're going to go first with CH3I. Then we're going to go with Ag2O and heat. And what are the products? Predict all products. Circle major. That's terrible. Circle major. So what happens first is the exhaustive methylation part. Pretty monochromatic here, isn't it? And not much to exhaustively methylate this one. You only have room for one methyl. And that's part one. And then two. You've got to identify the beta hydrogens or else you're in trouble. Remember, the nitrogen's the thing leaving. And that by definition makes any carbon attached to nitrogen an alpha carbon. That's our second alpha we ever saw in Orgo 1. And you got to remove a hydrogen from not the alpha position. That's not going to give you a pi bond, but from the beta position. So that's why I didn't label the methyl as alpha, because there's no beta in that one. And we got H's. What color should our H's be? Purple, why not? Purple, beta H, purple, beta H, and purple, beta H. Oh, I like my major from the bottom. It's the least hindered beta H is the one where there's no carbon groups attached over here. So we're going to make ethylene. And when you make ethylene, what's the other piece? Well, it's propyl, methyl, butyl, amine. That's one pair of products and it's major. The combination, okay, is the major. Now go from the one on the right side and you get ethyl, methyl, butyl, plus propylamine. And that's this one. Grab the beta H, make a pi, leaving group leaves. And on this one, you're going to make a pi here. Butyl, butene, methyl, ethyl, propyl. And that's the combinations that you will get. And that's the Hoffman in a nutshell. And our last one. I know what happened. I had another page when I made the new one. This one's inserted after. Here's our final topic for today. We'll explore that exhaustive methylation a little more next day. And in terms of what's called the Cope elimination, oh, once again, another guy's name, right? Cope. And there's a repeat offender here. Shouldn't say offender. It's a nice reaction. It's called the Hoffman. And yeah, we've seen Hoffman before. And it's the same Hoffman, although that's not always the case in organic chemistry. The name Hoffman, back in the early 1900s, there were many prominent Hoffman chemists, all different people unrelated to each other. There's been at least 2 different Hoffmans awarded Nobel Prizes. And so Hoffman's historically a profound name in chemistry. And the same guy did the elimination that did our Hofmann rearrangement, where primary amides underwent decarbonylation to make an amine. So he be careful. You got the Hofmann rearrangements, different than the Hofmann elimination, entirely different stories entirely. And Arthur Cope did the Cope elimination. And what happens during the Cope elimination is you've got to first create an N oxide. And there's a few ways to do that. You can use hydrogen peroxide or some kind of per acid like MCPBA. And we've got mechanisms for doing that here. If you use peroxide, you have an attack on the oxygen. And that, why would that happen? Well, it relieves these lone pair repulsions on adjacent oxygens, which is always what makes peroxides unstable. And then you have an acid-base step at the end, and you generate an N oxide. Or per acid does some interesting things. Gets an O, resonate, protonate. It gets rid of the H here as well. And there's your O minus. And you have an N oxide. Now what you have is what looks like a Hoffman situation where there's a base in a molecule that has a leaving group and beta H's. Your base is attached though, so you do not have to worry about things like kinetic control. The base is already in there. It doesn't have to approach at all. It's there. We just have to rotate a hydrogen around to grab it. And you will make what you would normally predict to be the major product. The one with the more substituted alkene will be major. And the one with the less substituted alkene will be minor, because this is all based on alkene stability. This one has more hyperconjugation. It'll be easier to make. It'll have a lower activation energy because it has more hyperconjugation. This has less hyperconjugation, higher activation energy. You make a lower amount of that one. And the mechanisms for elimination: the base grabs the beta H, sigma becomes pi, leaving group leaves. And there you go. Nice. Hydroxylamine is the side product. And I don't think I labeled those anywhere, did I? These are N-hydroxylamines. And that is the close to today's lecture. And we'll talk about what's called quaternary ammonium salts for our first segment next day, and what they're useful for and how they're easily made. And then I want you guys to have already waiting for me in my email box some potential review questions. I will try to get exam 3 layout to you maybe tonight, definitely tomorrow. And if I don't, somebody should send me an email reminder saying, please give me the exam 3 layout.
Professor?
Yes.
So exam 3 is going to be Monday or Wednesday?
We moved it to Wednesday. Wednesdays
So-
just are more convenient for us.
So we're going to have 2 review days?
We're going to have 1 3/4 review days, but yeah, pretty close to 2.
Sure. I have a question about the lab.
Mm-hmm.
So yesterday like we saw there's a lockdown for 3 weeks.
Oh, you already got that email, huh? I was wondering if they sent that. Yeah.
Are we still gonna go to the lab?
Oh no, don't come to lab. If you're one of my lab students right now, if you're in lab tomorrow, you're coming.
Mm-hmm.
Lockdown
But there's-
starts Wednesday and it lasts for 3 weeks. So Tuesday labs will meet tomorrow for the last time for 3 weeks. And Thursday labs not meeting at all, starting as of now for 3 weeks. All right.
All right, thank you.
And I'll send you more information as we figure things out, because everything's just, it's up in the air like it's been for a year, right? Okay.
All right, thank you.
All right. Take care, everybody. Be safe.